It's for you.
Thank you for your kind introduction, and thank you all for your kind attendance after a long week of this wonderful symposium, that you're still here listening to my talk at the beginning of the end of the symposium, so to say. My name is Philipp. I'm a PhD student at the Material Center Leoben in Austria, and I also want to express my gratitude towards my co-authors from MCL as well, Dr. Werner Ecker and Razumovskiy. From Montan University Leoben, my supervisor Lorenz, and from our company partner from Precipitate, Dr. Matthew Galler. And I also want to say a big thank you to Professor Tom de Bover and his team from Ghent University, with whom we're working together in this project. And starting so early in this morning, I want to start a little bit easy. We know that hydrogen in steels primarily accumulates at defects. It doesn't like to sit in the interstitial lattice positions. And how much hydrogen goes in and how it interacts with those defects determines which hydrogen embrittlement mechanism we get and how we should counteract that. And I want to make also some advertisement here. So we have recently been able to publish our multi-scale modeling approach from the atomic to the continuum component level scale in a nice book that you should see very soon, edited by Professor Mohammed Sikri. We, of course, you have seen in the title, it's a DFT study, density functional theory. I'm a simulations guy. So no experiments today, but I hope you can see that still with density functional theory, we can determine some very important ideas and concepts of how we can counteract hydrogen embrittlement. And I hope it now, and it's fine. So here, nice simulation, you put these two together, you get titanium vanadium carbide, as suggested in the title. And here already my question, which I introduced you, how does it affect hydrogen trapping? And we addressed this in a recent publication from earlier this year, Acta Materialia, where we not only investigated titanium vanadium carbide, but these also are very strong nitride formers, and nitrogen we always have in our steels. So we had a look at the titanium vanadium carbon nitride system. We modeled the alloying by use of disordered structures with optimized shorter and shorter parameters. And here already some of the first results. And I want to utilize this slide to introduce this type of plots to you, where we have on the base plane is our chemical space, with titanium carbide to the left, titanium nitride in the back, vanadium carbide in the front, and vanadium nitride in the back. And just if you don't believe what this PhD student has calculated, here these nice little crosses are literature results of other DFT calculations, and the brown X's are from experiment. And I don't want to spend too much time here on this slide, just to show you we calculate some physical properties. Why it's important is because they determine how many trapping sites we get from these carbides. Of course, DFT study, how we do it, we use Vienna ab initio simulation package. I think you are mostly not very interested in the specifics there, but just so you know, we assess a hydrogen trapping by the segregation energy. You might call it trapping energy, binding energy, determines probably from the field where you're coming from. Important to know is just with our definition, the more negative, the more attractive, the more negative the segregation energy, the more attractive a site for hydrogen is. And here you already see the bulk with some interstitial positions. We place hydrogen there with different chemical environments. And we already get the first glance on how hydrogen does like or not like to go into these carbides. So for the interstitial positions, I think it's no big surprise. Hydrogen doesn't want to go there. And it's also hugely dependent on the chemical composition. how much it doesn't want to go there, but that's not a focus today. I rather want to focus where it likes to go, which is the non-metal vacancies, so carbon or nitrogen vacancies. It's also no big surprise. We already know that these structures have vacancies and hydrogen may sit there. And it's also no big surprise that titanium carbide has the biggest attraction for hydrogen. And here I also need to mention that here we actually don't plot the global composition, but the local composition, which is the composition in the very vicinity of these hydrogen atoms, which is of great importance. And in principle, here you can see the chemical dependence of the hydrogen segregation to non-metal vacancies in these carbides. And of course, whether or not hydrogen goes in is a whole different story, but on the interface, it can always reach, right? And these carbides, when they precipitate coherent, and afterwards, when the misfit grows, they form a square network of misfit dislocations. And you can see here also how it looks like from the atomic scale. Unfortunately, this interface is a little bit too big for us to simulate. So we need to make some magic happen. And we can identify certain atomic arrangements that represent our misfit dislocations, the coherent interface and the misfit dislocation intersections. And here you can see the cell arrangements. You can see this nice colorful symbols are all the positions we sampled and put hydrogen in. And we have a pretty busy overview slide. So just focus on the coherent interface where, to save time, it's no big deal. It's what we would probably call a relatively shallow trap with up to like 0.31 electron volts, or roughly like 30 kilojoules per mole for those coming from experiments. And the interface vacancies, so non-metal vacancies, but directly on the interface, they follow more or less the same trend and the same magnitude as in the bulk, and could be classified as very deep hydrogen traps. And misfit dislocations and the intersections, they are somewhere in between, right? There are some moderate traps. They have a little bit of dependence on the chemistry around, and the misfit dislocations are on the like more shallow side of moderately deep traps, and the intersections are more on the upper side, on the more deep side. So having said all that, how we can now use that and combine that, we have hydrogen segregation energies as a function of chemical composition, and they determine our strength of hydrogen binding to a trap site. And we have physical properties which determine how many of these trap sites are there. And so we can now do a precipitate chemistry design to optimize our hydrogen trapping ability. And as a last thing, I want to quickly showcase how that could be done with the misfit dislocations intersections and the interface vacancies. So I want to first focus you to the left side here, dislocation intersections. And I also shift the plane to what we to 0.5 EVs, what we would probably think of as deep trapping. Marked here the area of deep hydrogen trapping, and you can see, starting from titanium carbide, it's close, but it's not a deep trap. So if we allow a little bit of nitrogen, we can make it a deep trap, the misfit dislocation intersection. However, we also lose a little bit of misfit. We have less misfit, and the misfit determines how many of these are per interface area. So that means we have a little bit of trade-off. We make it a better trap, but we have less of them. On the other hand, for the interface vacancies, they remain very deep traps over a whole composition range. So that means we can safely alloy, let's say, some vanadium here, make it a titanium vanadium carbide. It is less a deep trap, but nonetheless a deep trap. But what it brings us, if we look at the vacancy formation enthalpy, we lower vacancy formation enthalpy, means we get a lot more of these vacancies, and therefore get a lot more hydrogen trapping sites. And before I leave you with the conclusion slides, I want to thank you all for your kind attention. I want to thank you, our funding partners, and I want to leave you with three things. First, conclusion site, where you can put all this in relation to other existing traps. I want to leave you with an open mind for discussion. And I want to leave you with a take-at-home message. We can do precipitate chemistry design in terms of strength and number of hydrogen trapping. Thank you very much.
All right. Thank you very much. We have some time for questions. Yeah, please.
Okay, thank you very much, Philipp, for nice presentation. The question is, why did you need this kind of simulation of the vacancies and interviews, and also these different companies? Again, how do you say? Because in some of the other reverses, also including some studies that I did already, we have seen that the vacancies are inside, also in the mixed metal carbides. Inside the carbon vacancies, because then carbon the condition here is inside. But also I believe we have some substitution that can elevate vacancy that we have check it also. You have some confirmation by experiment.
Indeed, what I did not show is we of course checked vacancy formation enthalpy at the interface and in the precipitate bulk, and we see that it's a little bit more likely for vacancies to form in the bulk than on the interface. You're correct. Our hypothesis, what we can hope for, since vacancies are in the interface, if we can lower the vacancy formation enthalpy as much as possible, hopefully we might even generate a percolating network of vacancies, so we can ease hydrogen going inside the precipitate and activate, so to say, the bulk for hydrogen trapping, because otherwise it has huge diffusion barrier to go inside.
Yeah, one more short question.
So I assume you did our calculations in the what is usually the case in application. But are you planning to do finite element, finite temperature conditions to see how this change in larger temperatures?
Yeah, thank you for your question. Of course, indeed, you're correct. DFT is at 0 Kelvin. We need to keep that in mind. And there might be some shifts in the magnitude. I do believe that the general trend will be the same. It was originally planned to do also some estimation of finite temperatures. I cannot promise now if we have time or money for that, but I would like to do it, and thank you for your comment.
All right, so because of time, and thank you for your presentation and the question. Thank you. All right, so our next speaker is Mark Powers. Excuse me if I pronounce and not correct. It's about hydrogen assisted toughness reduction in pipeline steel from Ghent University.
Thank you for the introduction.